Okay, let's go for today's experiment on the diffraction grating, right? In this case, we have a diffraction grating means this diffraction has a lot slits, right? A lot slits. Usually, we have diffraction grating with thousands of slits, right, in 1 inch, correct? Okay, this is a formula that help us to work with diffraction grating. Is d sine theta equals m lambda, correct? D is the distance between two slits, right? The angle, right, is the angle from the slit to the screen. This is the screen right here, right? Screen, correct? And usually the angle is small, but when we increase the numbers of slits, right, the angle increases, right? Means that we can separate the fringes, right? We use this a lot in spectroscopy to separate the spectral lines, right, of a sample, right, of some spectrum, correct? And again, if we have spectral lines that are very close, right, we increase the number of slits, right, in the same, let's say, distance. So the function of the diffraction rate is to separate, right, the spectral lines. This function is similar to the function of a telescope, right, the resolution power. The resolution power, right, of a telescope is the same thing, right? It separates objects which are far away, right, and it looks like a one object, but when we increase the separation, the resolution power, right, we separate, right, these two objects and we resolve them. Yeah, that's the same function for diffraction grating in spectroscopy, right? Separate the spectral lines, right, and study, right, that spectrum better, correct? In the same way for a telescope, the resolution power. Okay, perfect. Now, in today's experiment, we have that we don't have too many slits, right, per centimeter, right? So the fringes are still are still close. In this case, we're dealing with a laser. Okay, so we create fringes, right? Constructive and destructive interference, bright or dark fringes. Okay, imagine that we're dealing with bright fringes. Okay, so we take several fringes, right? Let's say n equals to how many? 1, 2, 3, 4, 5, 6, 7, 7, right? 7 fringes. Now we take the distance, right, among those fringes, and then let's divide, right, that distance by n to have y. Y is gonna be the distance between two fringes. It's like at the average. Again, this is the case when they are very close. When they are separated, again, when we increase the numbers of slits or we decrease the distance between the slit, right, the distance increases. And we don't need to use this technique, right, because we can see clearly the distance between two fringes in this case, correct? But for this case, we have that the angle is small. Well, when that happens, remember we can use the approximation of sine theta is about tangent theta, correct? Now, if we construct a triangle right here, we call this L, this is Y, but we can create the angle in this way, so we have a right triangle. So what is the tangent of the angle? Well, it's gonna be Y divided by L, right? Y is the distance from the center right fringes, right, to any other fringe, right, up or down. Now that's Y, correct? Perfect. And again is the order number, right? Goes from 0 to 1, 2, and so on. Correct? Okay, now if we take m equals 1, because again we're dealing for the distance between two fringes, so we get this equation, right? Lambda experiment is dy over L, correct? From the theory, right, we're using a laser with wavelength 632.8 nanometers, and the distance, right, from the diffraction grating to the screen is about 3.15 meters. Okay, taking this into account, let's do three cases, correct? Case 1, the distance between two slits is 0.50 millimeters, D2 0.25 millimeters, and D3, right, 0.125 millimeter. Okay, to get a good measurement, right, for the distance between two slits, right? We use this technique again, using a group of fringes to find the average. Okay, let's do it. D, right? Let's find D. Let's take any number of fringes, could be 5, 6, and so on, right? And then this is a number right here. Find the distance, right, for that group, and then divide these two to find y, right? Like in this equation. Perfect. Now right here, let's go to the lambda experimental, right? Using this equation right here. Please put the equation right here, plug the values, right? And then compare this quantity to the theoretical value, right? Finding the percent error. Remember how to use the formula and then use the values right here. Correct? Repeat the same thing for the other two cases, right? Finding d and y, plug these values right here, right on that equation to find the experimental lambda, correct? And finally, the percent error. Okay, now let me show you again a picture that gives us the relationship between, let's say, d and n, right? I'm gonna give you the picture for the diffraction grating. Again, we have a ruler right here, right? You will see a ruler similarly to double slit interference, right? We have a ruler right here, right? And then we have the spots right here. So it's gonna be moving a little bit, right? Because I'm trying to adjust, right, to get the best picture for you on this ruler. Once you get the best picture, please freeze, right, in the computer, right, that picture and measure, right, the distance using this procedure, right? Finding d and n to find y, correct? Okay, let's do it. And it's gonna be a very interesting experiment, very similar to the interference. Okay, let's do it.